One can argue that the Arrovian social welfare setup is too demanding, and that is one of the reasons why we got the impossibility result due to Arrow. So, in the Arrow's social welfare setup, we are looking at a complete ordering over the alternatives as an outcome of that welfare function. Now, this could be very demanding, and the summary of the Arrow's impossibility result can be said in the following statement that achieving a social ordering. So, remember that this f of r is nothing but a social ordering. It is giving and taking as input all the preference orders over all the individuals, all the individual agents, and taking and giving out one complete ordering. Having this social ordering in a democratic way is impossible. That is what Arrow's impossibility result is saying. So, in order to mitigate this impossibility, there had been various attempts, and we will discuss about two such attempts in this module and then following modules. So the first setup is what is known as a social choice setting. Instead of an ordering, we are going to the function that we are going to define will be giving out only one alternative and not a complete ordering. And the second way of handling this is we'll see certain restrictions on the agent preferences. So maybe in practice, agents preferences cannot take all possible orderings over all the alternatives. They have certain restrictions, certain regularities, and if we can use those regularities appropriately, maybe we can get rid of this kind of impossibility results. So this brings us to the setup of social choice function. So the function that we'll be focusing on in this setup, the social choice setup, is what is known as the social choice function. Notice that the left hand side remains the same. The only difference is that now we are only considering strict preferences. Let's assume that for now. In the social welfare setup, we were looking at all preferences which also included indifferences, but here we don't allow for indifferences and we have only strict preferences. So if all these agents, all these n agents, have their strict preferences given to this social choice function, this function f will pop out one alternative rather than the whole ordering over that set of alternatives. So the most representative example could be that of voting or election. So let us spend some time in discussing various voting rules, because these are quite common and quite well studied, and therefore for our own knowledge we can actually know what are the different kinds of voting rules or election rules. So the first class of voting rules that we are going to discuss are called the scoring rules. So based on the position on which a specific voter keeps its alternative, so let's say we have alternatives A, B, C, and so on, and the corresponding score that one gives to each of these positions is given by S1, S2, S3, and so on. And when we are looking at the final outcome, we are just taking, so maybe for certain other agent, B may have a topmost position, A may have a second position, and C. Similarly, in that case, the score will be S2 and S3, S1, S2, S3 for those things. So if there were these two voters in this context, then B would have a total score of S1 plus S2. Similarly, A would have S1 plus S2, and C would have got twice of S3. So that is what this scoring rule means. So we define scores, and of course all these SIs should be at least as much as SI plus 1. So these scores are non-decreasing in nature, and there are various and whoever has the highest score, that alternative is selected as the final outcome. So certainly this is a social choice function, because we are taking individuals' preferences, we are only defining certain scores, and finally we are popping out one particular alternative, breaking ties arbitrarily. So there are certain special cases. The most popular one, or the things that we can the voting rule where we can associate most of the time, is what is known as plurality. you have the topmost position, the topmost score to be equal to 1, and all other scores to be equal to 0. So you just count the topmost vote, and this is exactly how we have our usual elections, the Lok Sabha or the Vidhan Sabha elections. So they have the voters only cast their most favorite candidate, which you can consider as giving the score of 1. For all the other agents, you don't really ask these agents, ask the voters to reveal them. So the veto is another type of scoring rule, where you have only one alternative which you don't want to include. For all the other alternatives, you have the same score of 1. Borda is named after a French mathematician who and also a social scientist who has given this this kind of a score, where you start with the m minus, if there are m different alternatives, you start with the m minus 1 of as the score of the first one, and then m minus 2 for the second one, and so on up to m, the final one. So the s of m minus 1 will be equal to 1, and the final one will have a score of 0. So this is how this Borda voting rule is defined. Harmonic has these scores to be the harmonic series, and for k approval you have the first k most preferred alternatives, which is having the score of 1, and for the rest m minus k you have zeros. That's the set of scoring rule based mechanisms. Now there are slight modifications of this plurality rule, which is known as the plurality with runoff. So there are two phases in this kind of a voting rule. In the first phase, all the candidates participate and people cast their votes in the usual plurality form, and then the top two candidates are selected, and then all the voters are asked to vote again. And this is so after the first phase, everybody except the top two has been eliminated. So some of the votes which were cast by the by certain voters whose favorite candidate has been eliminated, they are given another chance to pick one of the candidates from these top two candidates. And this is exactly what is done in the French presidential election. It is done using plurality with runoff. We'll discuss a couple of more voting rules. The third voting rule is the maxi-min. So what it does is it selects the candidate with largest margin of victory. Now, what is a margin of victory? This is the number of votes that you need to delete or alter in order to change the current outcome. So, for instance, A was currently being happening to be the winner. What is the minimum number of votes that you need to change in order to make someone else a winner? And that is called the margin of victory. In some sense, this is the closest opposing voter, opposing candidate whose votes can be altered. So if someone, so let's say A was beating its closest competitor by a margin of, let's say, 100 votes, and if that 100 votes could be altered, then you can make the closest competitor to be the winner. So this is something like the minimum number of votes in order to change the outcome, and you are trying to find out who has this highest margin. So that is the reason why it is called maxi-min. The fourth type is the Copeland rule. So now we can think about a pair of candidates and look at what happens in their pairwise election. So we remove all the, so we have the total ordering of all the agents over these candidates, and we look at pairwise, let's say A and B, and remove all the other candidates. So whether they are, so who is winning in this pairwise election? And if A wins the pairwise election with against B, then we are giving A score of 1. And similarly for all possible pairs, so all m-1 different elections, pairwise elections for that particular candidate, we are looking at who is becoming the winner. So Copeland rule is essentially who has the largest score based on that pairwise elections. That candidate is going to be the winner. Now, in this case, there is an interesting observation that one can make. Again, Copeland it's named after Copeland. Similarly, there is a idea of a Condorcent winner. So now what is a Condorcent winner? You can think of again the pairwise elections, and if there exists one candidate, one specific alternative which beats every other candidate in pairwise election, then we are going to call that winner a Condorcent winner. And it is not guaranteed to exist. Such kind of a Condorcent winner may not exist. And here is one example. So very simple example with 3 voters and 3 candidates. So maybe these 3 agents have this 3 preference orders over these 3 candidates, A, B, and C. What you can see is that A is beating B in a pairwise election. So A is above B in 2 cases and B is above A in only 1 case. So A is beating A in a pairwise election. Similarly, B is beating C in pairwise election. B is above C here, but C is above B here. So B is also beating C in pairwise election. But the interesting thing is C is also beating A in pairwise elections. So there does not exist any specific candidate who is beating every other candidate in pairwise election. So therefore, a Condorcent winner might not exist. But we can define something like if there exists some preference profile where Condorcent winner exists. So of course, this is one counter example, but you can also create certain examples where the Condorcent winner actually exists. If that Condorcent winner exists, then the voting rule, those kind of voting rules that returns that Condorcent winner as the outcome, those kind of voting rules are called Condorcent consistent. I mean, the name itself is saying a lot. So if there exists a Condorcent winner, then the voting rule will give that Condorcent winner as the outcome. And it is not very difficult to see that Copeland is going to be Condorcent consistent because of the very reason that if there exists a Condorcent winner, that means it is winning all possible pairwise elections, then that particular winner or the candidate will have a score of M-1. It is beating everybody else in pairwise elections. Now, if you look at any other candidate, that candidate will have less than M-1 score, because it is at least being in the pairwise election against that previous candidate who is the Condorcent winner. It is losing against that. So it can win at most M-1 cases, but it will lose definitely to that candidate. And therefore its score cannot beat the score of that Condorcent winner. So therefore Copeland will give that Condorcent winner the highest score, and that will be the winner. So that's very standard. I mean, Copeland is essentially Condorcent consistent by its design itself. But some of the voting rules that we are quite familiar with, we use it quite often, that is not Condorcent consistent, and this is sort of a fallacy in itself. The plurality rule is so much used in all possible cases, it does not satisfy this very idea of Condorcent consistency. So Condorcent consistency is something like very natural thing, right? So you are looking at a candidate which is beating everybody else in pairwise elections. It will be very unjustified for a voting rule not to select that candidate as a winner. But you can see that in plurality it does not happen. So here is an example. So suppose there are again 3 different types of voters. By type I mean that their preference profile remains the same. The preference ordering among these 3 candidates remain the same. So 30% of these voters prefer A over B over C. The other 30% thinks that B is above A is above C, and there is 40% which thinks C is above A is above B, right? Now if you look at the pairwise election situation, you see that A is above B in 40 plus 30, that is 70% of the case. So A beats B in pairwise election by a score of 70 to 30. Similarly, A also beats C. Here you can see that A is above C for this 30% and 30%. So it also beats C with a margin, with a margin of 60% to 40%. Now, clearly A is the Condorcent winner because it beats all other candidates in pairwise election. Now, if you look at the plurality rule, so plurality rule just looks at the topmost vote. So every agent, every voter is asked to cast its ballot for their most favorite candidate, and in that case, A will get only 30% of the vote, B will get 30% of the vote, C will get 40% of the vote, and therefore C is going to be the winner in plurality, which is not the Condorcet winner. Condorcet winner was A. So actually you can prove it even more generally. You can create counter examples for any kind of scoring rule. So no scoring rule based mechanism that we have discussed in the beginning, all this plurality, veto, border, harmonic, K approval, none of them are actually Condorcet consistent. This is quite amazing. Okay, so let us now go back to the social choice functions setup. We have this function f, which is mapping the individual preference orders to this set, to the set of all alternatives or all candidates. Now we are going to define a few things, few notions which will be useful for developing the conditions and the results involving social choice functions. So the first thing is Pareto domination. So we can call an alternative A to be Pareto dominated by B if very naturally that alternative is strictly dominated by B by all the agents. So B is strictly preferred to A by all the agents. Now we talk about Pareto efficiency for a social choice function. So we call a social choice function to be Pareto efficient if there exists if for every preference profile where you have a dominated alternative, then that social choice function will never output that dominated alternative as an outcome. So in every preference profile, let's say A is Pareto dominated, then the f of P can never be equal to A. So, which is quite natural. Why should the society choose an alternative which has a better alternative than that one by all the agents? So, Pareto efficiency is the first property that we will be looking at, and unanimity, the name itself says what it is. So, we are going to call a social choice function to be unanimous if you have a preference profile where the top alternative of all the agents are the same. So they agree on the topmost alternative, then the outcome should also be the topmost alternative, right? So this is what it means, that if the topmost, so Pik is the kth preferred alternative of this agent I. So P11 means it is the topmost alternative, the most preferred alternative of player 1. Okay, so that is unanimity. Now we can actually start drawing relationship between this Pareto efficiency and unanimity already. So we observe, and I claim that Pareto efficiency will imply unanimity. So what does that mean? That if we have a Pareto efficient social choice function, that should also be unanimous. Why is that? So we'll have to show, so suppose we start with a social choice function which is Pareto efficient, we will have to show that that is unanimous as well. Now for unanimity, the if condition itself is that this is going to be, the topmost alternative is going to be the same for all the voters or all the agents. So let's say that is given to you, that the topmost alternative is the same. And now my social choice function is also Pareto efficient. That means it will never output an alternative which is Pareto dominated. Now because A is the topmost, then A actually Pareto dominates all other alternatives. So you cannot really pick any of the other alternatives apart from A, because that is Pareto dominated by A. So if you just rule out all the possibilities, the final thing that you have you are left with is A, and therefore f of p has to be equal to A because of the property of Pareto efficiency. So which is essentially nothing but unanimity. So if we have a Pareto efficient a social choice function, then we can show that that is unanimous. And we have also used this strict containment. That is, Pareto efficient is a strict subset. The social choice functions which are Pareto efficient is a strict subset of the unanimous social choice functions. Why is that? So you can consider, I mean, breaking the condition of unanimity is very simple. You can, of course, whenever you have the top alternatives to be the same, the social choice function should be equal to A. But imagine a situation where all the topmost alternatives are A, but except for one agent, let's say B. And for that, A lives somewhere below, and maybe there is C. And C is possibly a Pareto dominated by A. So for this kind of a preference profile, you cannot really apply, I mean, it could be unanimous because it does not satisfy this condition. So the social choice function can actually output something. And let us assume for this particular this particular preference profile, f is actually outputting C, which is a Pareto dominated thing. So this f is not violating the condition of unanimity. Whenever all the topmost positions are same, then f of that preference profile should be equal to that topmost alternative. But when it is not, even if you puncture one preference order of one agent, you pick something which is Pareto dominated, and that is not Pareto efficient. That social choice function will not be Pareto efficient, even though it is unanimous. So that is one example why this containment is essentially strict. Okay, the third definition that we are going to discuss is that of ontoness. So we are going to call a social choice function to be onto, and this onto is just the natural normal definition of function ontoness. That for all alternative A in A, so lowercase a in the set of alternatives, there must exist some preference profile P of A, let's say, in that script P whole to the n, such that if you apply f on that, you get back that alternative A as your output. And this is also very similar. I mean, this implication of unanimity implying ontoness is pretty straightforward. All that you do here is pick the A on top, and because of unanimity, you will always output the F will always output for this kind of a preference profile the outcome of A. So no matter whichever alternative you pick, if you pick B, you can replace all the topmost positions with B and apply unanimity, and you will get B as your outcome. So therefore it is that F will always be onto, so therefore unanimity is also going to be onto. Now you can I can leave this as an exercise to show that this containment is also strict. So you can have some social choice function which is onto but not unanimous. So let's try doing that. Okay, so let us move on to the next definition, and this is the place where we are actually talking about strategic behavior. So manipulability. We haven't thought about manipulability when we talked about the arrow's impossibility result. In particular, even before that, when we were discussing the revelation principle, we had actually spoken about the manipulability. So let us get back to that point in this domain of social choice functions. So we are going to call a social choice function f to be manipulable if there exists a player and a preference profile P such that for that player I, if that player is misreporting its preference to be Pi prime, and other players are actually choosing their corresponding P minus I, then it is better for that agent. So you know that this outcome, this f of Pi prime P minus I, is one outcome. Let's say this is A, and this outcome is B, so then by misreporting it is getting an alternative which is more preferred than the outcome if it was not misreporting. So we have seen this kind of a definition in the context of cardinal preferences, and this is ordinal preferences, about dominant strategy incentive compatibility. So you can just invert or negate this statement of non-manipulability. In that case, what you will get is that for all agents I and for all profiles P, the inequality, so this will essentially flip, that is, you don't get, so f of pi comma p minus I should be at least as good as f of pi prime p minus I. That we have already defined as truthfulness or dominant strategy incentive compatibility. Here we are defining it in the reverse way, that is manipulability. So when we are talking about manipulability, let's look at some examples how some of these known voting rules can be manipulated. So again, the usual suspect is plurality. So let's say that we are having this plurality where we are just asking each of these agents to report their most valuable, most preferred candidate, and we are counting how many of them are there and breaking the tie in favor of A over B over C. So let's say there are 4 voters who are having this kind of a vote, 4 voters who has this kind of a vote, and there is exactly 1 voter who has this kind of a vote. So what is happening is that it is being tied between A and B, and this particular individual, this last individual, is sort of a tiebreaker. Now it sees that if it reports its vote truthfully, then according to this tie-breaking rule, A is going to be the winner, which is its worst preferred alternative. Instead, if it changes its preference to B, it votes for B, then what it gets is at least better than that. It knows that C has no chance of winning in this plurality vote, and it chooses to vote for its second best candidate, and therefore it is manipulable. You can see this by this definition. You could already find some pi prime for this particular agent such that it gives them a strict better payoff, and this is something that you have possibly seen or at least think about seeing this kind of a situation in real elections. The second case is about Copeland. Now plurality, we know, because this is a scoring rule based mechanism, this is not Condorcent consistent, but Copeland is Condorcent consistent. Again, the tie-breaking rule, we know that it is in favor of A over B over C, and what we are going to see in Copeland mechanism, Copeland voting rule, is that we are looking at pairwise elections, and we are giving scores for that. Now A beats B in pairwise election but loses to C, so therefore A has a score of 1. Similarly, if you look at B and C, you can see that their score is also 1. So if it is truthful, so if all agents are revealing their preferences truthfully, then A is going to be the winner, because that's the tie-breaking rule. But now you can see that this particular individual, and here there are exactly 1 voter in each of these classes. So A is the least preferred alternative for this agent here, and if it reports, let's say, C above B, so then at least it gets C to be the winner, because in that case C will beat in a pairwise election even B, so C will be the Copeland winner, and therefore C is at least C is a strict preferred alternative than A, which was going to be the winner otherwise. So we can see that, again, according to the same definition of manipulability, we found pi prime for this particular agent, which essentially is beneficial for it than its true preference ordering. Okay, so we are going to call that a social choice function to be strategy proof. This is the term strategy proof we are coining for the first time. Yeah, we will be using this interchangeably with truthful, incentive compatible, and so on. So strategy proof, if it is not manipulable by any agent at any profile. So essentially, we'll have to negate this statement, the manipulability statement, and we can write an equivalent statement accordingly. And as we have discussed, for all I in N and for every profile P, the opposite of this this implication should hold. So what is the implication of strategy proofness? Let us define a few things in order to understand this. So we define what is known as a dominated set of a specific alternative A at a preference of Pi. So as the name suggests, these are the set of all those alternatives which are below A in this preference profile, in this preference Pi. So let's say in this example, we have this alternative D, and this dominated set of D under this Pi is nothing but A and C, which are below that particular alternative in this preference order. So that is what it means. This is the formal definition, and this is an example. The second, the other definition that we are going to use here is that of monotonicity. So what is monotonicity? We are going to call a social choice function to be monotone if for any two preference profiles, let's say P and P prime, with in the first preference profile, the outcome or the social choice function outcome is going to be equal to A, and this dominated sets are essentially increasing in its size. So if we go from Pi to Pi prime, we see that the dominated set, all the candidates, all the alternatives that were below A in Pi continues to be below A in Pi prime. There could be some new alternatives which are now going below that. So in some sense, A's relative position is actually weakly increasing in Pi prime than in Pi. Then this monotonicity is saying that f of Pi prime should also be equal to A, and this should hold. So this dominated set condition should hold for all agents in I in N. So every agent is now having more alternatives which are worse than A. So if we already have outputted the social choice function has outputted the alternative A, then why it should continue to output it even in this new preference profile. That is what monotonicity means. So here is one example. So let's say this is our P. So for all the different alternatives, for all the different agents, these are the positions of A, and this is in P. And in P prime, what is happening that they are actually climbing a little above. So maybe A is climbing above. So that means some of the other alternatives which were here, let's say B or C, they are now coming down and sitting below. All the alternatives which were below it are always, they still remain below A. And similarly here for all the agents. But now new, possibly some new alternatives are also coming below that. So A's relative position in this is weakly increasing. So if so the monotonicity is essentially saying this, if f of P was A, so in this preference profile, if your outcome was A, then here also you should have A as your outcome. If you apply F to it, it should output A, and that is monotonicity. Now let us conclude with one result, and we'll prove it next time. If a social choice function is strategy proof, then it implies and is implied by monotonicity, if and only if condition.